We'll first have some brief review of the set theory. I believe most of you have learned that maybe in high school or somewhere. So the set theory. So you are familiar with that, right? Okay. Yeah, we will have. If you kind of forget, that's fine. We will have some review today. So it should be fine. So why we're reviewing the set theory? Because this is a very basic for the formal specification. Because as you know, when we are trying to learning something, maybe modeling, specifying something in the computer world, okay, we will need, when doing some operations, usually it's a set of stuff like a set of names, right? Like a set of names, a set of you're deleting a set of names from the list, or you are adding a set of stuff, or you are doing maybe calculation to a set of numbers. So usually when we're doing operations, we are dealing with a whole set of objects. So set is one important thing, and the other important thing why we're learning this set, it's more convenient than those mathematical languages. Those symbols, we can use that. You can use them in our specification language. So it's more formal way of specify those objects. So that's why set is actually an important basic. It's an important base of thank you for us to learn the formal method. Okay. I don't know. Do we have a whiteboard? Whiteboard is over there. That's okay. I will try to type it here, so that because I'm also recording this class, so that I can upload it to D2L. In case you forgot, you maybe distract sometime, or you missed the class somehow, you can go online and check for the videos. Okay. All right. So let's get started about the set. So let's start with the definition. What is a set? Yes.
Set is a set of values within two boundaries. So it could be integers, natural numbers, real numbers, anything like that.
Yeah. So basically, set. It is a collection of objects. Yeah, you're right. It is a collection of objects, and within a set, usually this object within a set, they need to have something in common, so that you can describe the set with like nature numbers. Okay, a set of nature numbers. Of course, you cannot just list a whole set of nature numbers, right? Or maybe a set of images. That's fine. Maybe a set of a pair of image and its label. It could be a set. So a set of pair, something like that. So it's pretty flexible. You can define your set a lot of ways. Okay. So by saying a collection of objects, those objects, it can basically be anything. Yeah, especially if you are dealing with software engineering, you are dealing with modeling a software. Usually, maybe it's a set of data, right? It's a set of, if it's a database system for the classroom, it can be a set of names of the student, right? Or it can be a set of the student object. maybe the student object, it can contain the names, IDs, your status, grade, your address, phone number. It could be that, a set of student object. Okay, so that student object, object-oriented programming, the object, it can be anything you define, right? It's kind of a set of computer. Maybe it's more solid. Maybe it can be abstract, a set of objects that is virtually maybe defined. It can also be a set. So a set can be a set of anything. Okay. Yeah, and by using the set, we all have another convenience. Using the set is, as I mentioned, the set has the object in the set, they have something in common, so they are basically of the same type. Sometimes when you are doing some operations, you have to do it for the object that is of the same type, right? Like you can when you delete the names, you can only delete names. You don't want to delete the other informations. If you, things like that. Okay, so let's try to type it. So basically, we use the curly brackets to define that set. Let me see if I should type it here. Yeah. So we can use this to define a set, and within the set, you can have maybe this numbers 1, 2, 3, just like that. So this is the set of 3 numbers, 1, 2, 3. You can say maybe it's nature numbers, or it's integer, something like that. But it's not a whole set of integer, or it's not a whole set of nature numbers. But this defines a set. Within that curly brackets, there are different elements of that set. Okay, and one important feature, attribute of the set is, let's see if you remember that. Can we have a set like this? Can we? So we have duplicate in a set. I don't know where you heard that, but actually it's not allowed here. Yeah. So it's that duplicates are not allowed in the set. If you learn that it is allowed somewhere, I don't know, you put it in that course, but in this course, duplicates is not allowed in the set. Okay, in formal specification. That's an important property you need to remember. No duplicates in the set. Okay, so like this, something like this, it is not example of set we're talking about here. It's not eligible set we're talking about here. So because there is duplicates here, so yeah, you cannot have another 2 over there. Also, you can contain aggregates of object, like what I mentioned, a pair, right? Maybe it's coordinate 1, 2, and then another one is 3, 8. Okay. Another one is 6, 10, things like that. So you can see, so for each element in the set, they are separated by this. Okay, but for those elements, it can be another aggregate. So it can be a pair. like 1 2, a pair of numbers 1 2 3 8 6 10. It may define a triangle. I'm not sure if it defines a triangle, but it's a maybe 3 point within in a space. It can define the 3 points of the triangle. Yeah. And what I mean is just it can be aggregates, and also if it can be vector of 3 1 2 10 here 1 2 5. If we look like 3 3 2, probably it won't be a eligible set, but it depends. Somehow if you need to define yeah, I don't think you can define a set like this, right? So you have to have the same amount of elements within each aggregate. Like if you put 100 here, it's fine. Yeah. So it can be a aggregate of stuff. Okay. Yeah. So that's how you define the set. All right. And this is a number. Maybe it can be a student 1, student 2, and student 3, something like that. Just they have to be of the same type. Student 3. Okay, let's see. Student 3. So this is kind of like a set of student pair. Okay. So I just mentioned you cannot have duplicates there. Let's see. How about this? Student 2. Is this okay? Huh?
Make it bigger.
Oh, yeah. I mean, see if I can. How can I make it bigger? This better? Yeah. Cool. Is this okay?
Yeah.
Yeah. How many of you say that's okay? Yeah. So why do you say this not okay? Yeah.
I'm okay.
Okay. Cool. Yeah. So this is okay because although we have a student 2 here and here, but this is not a set of student. Okay. This is a set of the pair. Maybe a group. Maybe it's a student pair. It's a group of student, a set of group. Maybe the student can participate in 2 groups, but it's okay, because as long as the pair do not duplicate, then it will be fine. Yeah. So student can appear in maybe multiple groups, pairs. So this is fine. Okay. Also, a pair, it can be a finite or infinite pair, like what I mentioned. So maybe a 1 2 3 is a pair, as a finite pair. You can list all of them, but there are some sets that you cannot just list all of them, like the nature numbers, right? Integers, you cannot list all of them. Yeah. Okay, so the objects in the set, we can call it elements, or we can call it the member of the set. So any terms I use, it refers to each individual members or element in the set. In this case, it's a pair. It's a pair. Okay. And some other operands here. I don't know if I can type those in. Okay. Let me see. All right. Okay, so if we are saying some members that appears in a set, which means that members belongs to, is a member of the other set. We have a symbol here. Yeah, we use this symbol. Okay. Okay, let's give an example. Like 1 is a member of the set. Okay, 1, 2, 3. Okay, so this is true, right? This predicate is true because 1 is a member of this set. 1, 2, 3. Right, it's pretty straightforward, nothing weird, nothing tricky. And if you want to say 10, if you want to say 10 is a member of 1, 2. So this predicates will return false because this is not true. Alright. But if you change that, I don't know how can I put a slash there. So if you put like a slash on this symbol, it means maybe 10 not belongs to this set. That will be true. Okay. I'm not sure if I can find a. Oh, okay, it's here. Nice. Yeah. So this is true. Okay. Yeah, it's pretty straightforward. Okay. Yeah. So this is the basic thing of the set, and then let me clear this up. Okay. Then we will learn how can we specify a set. What we just learned is just we list every members there. It's good for maybe some finite set, like a set of nature number less than 10. Okay, it's fine. We just write down like 10 numbers from 0 to 9. Okay, is 0 a nature number? No. Yes or no? Actually, it is. The first time I learned that, my teacher told me 0 is not a nature number, but after several years, another teacher told me 0 is a nature number. It belongs to the nature number. And I actually checked that. 0 is actually a nature number. Remember that. Yeah. Okay. So, it is a nature number. Hey, how are you? So 0 is a nature number. So if I say a set of nature numbers that is less than 10, which means it is from 0, 1, 2, 3, 4, 5, 6, 9, 5, 6, 7, 8, 9. Okay, 0 to 9. Okay, it's okay if we can list that. Okay. However, if we want to say the set of nature number, how can you do that? How can you specify that? Or that's infinite. Let me give you another example. Maybe a nature number that is less than 10,000. It still take a while if you want to list all of them, and it's tedious work. It's a waste of time to list all of them. So we have some way that we define the set so that we don't need to list all of them. We can just specify the elements. We describe the elements in the set. Okay. Yeah. And sometimes if it's infinite, it's impossible. If it's a large set, list everything will be tedious. Yeah. Okay. And sometimes we'll list a set. It can be ambiguous as well, like yeah. 1, 3, 5. When I give you this set, okay, 1, 3, 5, how can you describe it? If you want, just use a nature language to describe this set. What?
Set of odd numbers.
Yeah, 3. Maybe the first 3 odd numbers, right? First 3 odd numbers. That's one way to define it. And the worst thing is we can have multiple ways to define it as well. Like the first 3 odd numbers, and you can define like it's the square root of this set. 1, 9, 25. Okay, you can define at this. So it makes things ambiguous. One of the important motivation we're learning this formal method specification whole thing is we want to eliminate those ambiguous. 'Cause ambiguous sometimes it kills the a lot of possibilities for maybe for the computer to understand. For computer to understand one thing, you have to eliminate the ambiguity for sure. So this is not a good way. Listing is not a good way. So to cope with this disadvantages, we have a notation that enables a set. Sorry, that enables this set to be defined unambiguously, like this. If we still want to define this like n, let me write it down first. Okay. Okay, so this is the way we define a set. Okay, so we here we have a 3-part that we need to learn. Okay, in this notation. First it is this side. So we define an n as anything from this this big N is actually the natural numbers. Okay, so N is the natural number. That's one thing. And after here we have, before this dot, we have maybe some conditions, restrictions here. So N squared less than 25. N squared less than 25. And then after this dot is an N. After this dot is the actual thing that is in this set. Okay, you know what I mean? So this actually defines the natural numbers that whose square is less than 25. So it's a set of natural numbers whose square is less than 25. So it will be something like 0. Yeah, assume 0 is the natural number, because I know somebody may be against that. 0, 1, 2, 3, 4, but not 5. Okay. Yeah, not 5. So actually this defines this. Actually this set definition defines the same thing as what we listed here. Okay, and after this dot, this N is actually that member in this set. So 3 parts. This part is called a signature. Okay, this part is called a predicate, and this part is called a term. Right. So so the signature is actually consists of a series of identifiers together with the set to which they belong. So you can define another way, like N and M. N and M, they are all natural numbers. Okay, and then we have a signature like this. We have a predicate like N squared less than 25 remains the same, and the term is N. This actually also still defines this, but actually we put M here, it's meaningless. But if what we do is N M, this actually makes it become an infinite set. It is a set of pairs that consists of the N, which is 0, 1, 2, 3, but the M is anything, basically everything in the natural number. It can be 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6. It's kind of but usually this is not the case, so we will define like this, and M 3. Okay, so can anybody tell me what this set looks like if you want to list it?
So I think what it says is we define N and M as a natural number such that N squared is less than 25 and M is less than 3. And N and M is within that set.
Yeah, so what is a set looks like? It's a set of
M is, so I would say
Yeah, it's a set of pairs. It's a set of pairs, right? So this set will looks like this. Because mn, right? M is basically, I don't want this. I don't want this. This is gonna be easier. Okay, n is basically 0, 1, 2, 3 numbers, and m is 0, 1, 2, 3. So 0, 0, right? 0, 1, 0, 2. No, just 0, 2. And then it's 1, 0, right? One, 1, 2. Yeah, I think.
We have 0, 3.
0, 3? No, because m is less than 3, so 3 is not included.
So if then n is less than 2, so 2 should not be included.
Yeah, n is less than 2. Yeah, this is n, right? At the left side is n. At the right side is m. We define this here, n, m. It's a pair of n, m. Okay. So anyone still need some more explanation here? Okay, so so here what we define is m and n and m, they belongs to nature numbers. Okay, so if we only look at here, it's from 0 to infinite, right? But then we give some conditions here, restrictions here, that we restrict n. It can be only less than 2. The nature number is less than 2, right? So n can be only 0 and 1, all right? And m can only be 0, 1, and 2, right? So like n is like 0, 1, 2, 0, 1. M is like 0, 1, 2, 3. No, 1, 2, 3. Okay, then we want make pairs of all of them. So the pair is because n has 2 possibilities, m has 3 possibilities. 2 by 3 is 6, right? So together, if we make them pairs, we have 6 different kinds of possibilities. So it's like we use this, we select 0 from here, and then we select 0 from here, so it's 0, 0. The second is we select 0 from here and 1 from here, we make it 0, 1. Then we select 0 from here and 2 from here, we have 0, 2, right? And then we finish this 0 here, and then we start with this 1. We have a 1, 0, 1, 1, 1, 2. So that's a pair. Okay. So this whole expression will give you this kind of set. Yeah. So n, m. Okay. We describe n. We tell you the signature. What is the n and m, and then we give you some conditions, maybe restrictions there. To refine this, okay, we don't want to make it pretty big and huge. It's meaningless sometime. And then after this dot, it's actually the term which defines what is actually the members, or what are actually the elements inside, the forms of the elements inside this set. So in this case, it is a pair. All right. Right. But if I define it as n time m, so what is actually inside the set? What the set looks like? Can you mind tell me?
With multiplication of the values and
Yeah. So basically, still here, we pick every possible pair of n and m, and we like multiply them together. Like here, yeah.
Wouldn't that create duplicates? Be 0?
Yeah, it can create duplicates here. Good question. Yeah. So after here it's 0, 0, 0, and here this is also 0. So 1. This is 2. Okay. So yeah, as you notice, there are duplicates in this set, so we only need 1 0 here. Actually, the set looks like this, because since the duplicates are not allowed in the set, so if you have more zeros there, that's actually the same thing. It refers to the same thing, 0. No matter how the 0 is counted, it can be 0 times 1, 0 times 2, 0 times 3. But they all refer to the same thing, 0. So 0 is like the only, we can have only 1 0 here. Yes?
You're using a conjunction with the carrot top in your symbol.
Here?
Yeah. Do you have good definitions for conjunction and disjunction?
This is actually an end. Just make it like end. It's not yet. We're not using this union thing yet. So this is actually, you can just say it as end.
Oh, and?
Yeah, end.
Oh, okay. I thought you were doing
Yeah.
conjunctions and disjunctions.
Yeah, this is an end. Okay. And yeah, 0, 1, 2. Okay, another important thing, do you think there's an order in a set? Order. Does order matter? Like 0, 1, 2.
No, I don't think
1, 2, 0. Are they the same set? Yeah, yeah. Yes, exactly. That's a set. Okay. So in the set, there's actually no order. Alright. If you want order, actually there's some other things. Maybe if you're familiar with data structure, maybe a vector. A vector, it actually has an order. Yeah, vector has an order, but set, no. They're all the same, no matter which one you put first or last. Yeah, it's the same. No order. Okay. Let me see if there's something else. Okay. Then we'll have another thing here. Let me explain. Also here, it can be different form, different term here. It can be pair. It can be the production of this multiplication, or it can be a plus or some other operations here. So it's flexible here. Basically, you can basically you can use that to express what you want to express in the specification. Okay. All right, and then let's go to the next. Okay. So that's a purely mathematically how we are defining the set. So here's another example that we use this set. How we use that in like under a scenario of modeling maybe a system. Okay. So for example, if we have a lot of monitors in the building, for the buildings in the monitor, okay, for the monitors in this building, we define this as the okay, maybe a set of monitors. Okay, so mon is a monitor. Okay, that belongs to this monitor set. So this set may be defined somewhere. It just refers to all the monitors in this building. Okay, suppose this set, this monitors is a set that refers to all the monitors in the building. Okay. So here, suppose we have a function monitor state. Okay, which returns the true or false. So monitor state is actually a function which take two parameters. The first parameter is which monitor. The second parameter is the state. So the state of the monitor can be on and off, simply speaking. Make it simple. On and off. Okay. So if that monitor is on, you give monitor, and on, it will return the true. Okay. If that monitor is off, you give a monitor, and off, it will return true. Otherwise, it will return false. If you check, okay, say this monitor, is it on? If it's off, it will return a false. And if you check if this monitor is off, but if you check with this on, it will return false. Okay, so it check if that monitor is on, simply speaking. And then we have a dot here, and then it's monitor. So can anybody explain this with a natural language?
Natural language?
Yeah, natural language.
Wouldn't it be 1 or 0? So it's either on or off. So it'd be monitor. Mon is a monitor such that monitor state checks the monitor, and then on value.
Yeah. So remember what we just mentioned here? It's a signature, right? MON is monitor. It's a monitor.
MON is.
Yeah, it is a monitor. MON is a monitor. And then we give restrictions. Monitor that is on. Okay, monitors that is on. Then the form is actually the MON. So what is this set? Oh, what is it?
Just one.
Just the one? Yeah, maybe not. It depends. It can be one monitor. It can be just one monitor, but it can be something else. Okay, so let me explain it. So 3 parts. First, MON is defined as a monitor. It belongs to the set of the monitors that is in this building, okay, or maybe another building, but it belongs to this monitor set, okay. And this actually, because there are a lot of monitors there, right? A lot of monitors in this building, maybe hundreds of them. But this gives you a restriction on those monitors, right? So what restrictions give is, we want to make this true. If we want to make this true, if this function returns true, which means that monitor is on. That monitor is on. So first we have a whole set of monitors. Then we restrict it to a subset here. Those monitors is on. Okay. And then after this dot, that's the actual element inside this set, right? So it is a set of monitors that is on. Alright, so this will give you a set of monitors that is on, or yeah, it depends on what this set is. If we assume this monitor set is the monitors, all the monitors in this building, this set will give you the monitors that are on in this building, or the monitors in the building that are on. Okay. If we put this like off, what is that?
All the monitors that were off.
Yeah, correct. If we put this as off, it will be the monitors that are off in this building. Okay. Yeah, so this kind of operation is pretty useful in when you're modeling your programming, your system, right? Computer system, right? Because maybe in some operations you want to get all the monitors that are on, because maybe you want to search for something. Then this is something that helps you specify that monitor. Yeah.
So how will you write the set? Suppose you were given this problem. So how will you write the set?
You want to list all the sets?
Yes.
Yeah, it can be a monitor. Usually you don't have to list it. Maybe monitor 1, monitor 4. It's just an example. And monitor 5, maybe monitor 2 and 3, they are closed. It depends on which monitor they are closed, which monitor they are opening. So
how will you differentiate it from the monitor that off?
how will I
Yes. How will you differentiate it from monitor that off?
off? Yeah, so this is on, this is off, this is on, right? So if you put this actually a set of monitor that is off. This is a set of monitor that is on. So it depends in the system. So this is the definition or specify that, like we describe that monitor, that set, because not all the set you can list them, right? Because the set may be changed. It's changing, right? Because maybe during the night we have all the monitors on. Maybe in the morning we only have half of them on. As possible. So this, if you want to list them, it's not possible, because it's changing, or it's infinite, right? Because maybe we will add more monitors. We don't know. But if we want to describe it, yeah, if you want to listen, you know that maybe at this moment we have 15 of the monitors that is on. We can list maybe it's from monitor 1 to monitor 15. It's okay, but that specification is horrible because that specification is only used for, it's not dynamic. Okay, it's only used for under some circumstances at that point, right? If you want to do some operation, like I want to turn all the monitors that is off, I want to turn them on, then I will use this specification, right? Or I can say, maybe I know that only monitor 2 is off in the building. I can say turn monitor 2 on. But that kind of operation is restricted to only that time, that point, right? After the monitor 2 is on, if you still turn it on and on again, that's meaningless, right? So if you want like to say something like turn the monitor that is off on, then you need to use this to specify that monitor is off. Okay, so this is like a description. So they all have some maybe a mapping to a natural language. But natural language, that's what I mentioned. Natural language first. For computer to understand natural language, it maybe a lot of, I know the AI is powerful. Maybe a computer can't understand some natural language, but the ambiguity is something that kills it. So, but here it eliminates the ambiguity for computer to understand this specification. Okay, that's why we are having this formal specification here. Okay. Okay, and let's have another set. Suppose we have set like this: 3, 5. Okay, suppose we have a set like this: 3, 5, 7, 9. Okay. If we are trying to describe it like this, is a listed set. Okay. So if we want to describe it like what we use with signatures, predicate, and the term, like those things, those 3 parts, how will you suggest me doing that? So 3, 5, 7, 9. It's not natural numbers. They are natural numbers, but can we define some other way? But it's not continuous natural numbers, right? How can we define this? Describe it. First, how can we describe it in natural language? Can you describe it in natural language? Huh? Yeah, they're odd numbers, but that's not all the odd numbers, right?
Odd numbers greater than 1 and less than 10.
Yeah, exactly. So that's the natural language. We describe it. So that's the odd numbers that is greater than 1 and less than 10. Yeah. Nice. So if we want to define it, like let's use n. That's fine. So it's odd numbers, and then we give restriction. N is greater than 1, right? And n is less than 10. Then we have a dot n. Is this correct?
Yes.
Yes. Yeah. Good. This is correct. Or another way is like we use greater or equals to 3, or like less or equal to 9. Yes, exactly. Nice. Okay, so that's how we describe it. So it's basically a listing, a transformation from a list of maybe elements to maybe you think about it in natural language, logic, and then you describe it mathematically. Once you describe it mathematically, you have the power to let the computer understand it. You have the power to specify it, to eliminate the ambiguity. Yeah. And then you have maybe next class we talk about, when we talk about the advantages of using formal specifications, you know you're maybe more motivated to write them out in mathematically. Yeah. All right, so that's how to describe this set. Okay. Another thing I want to mention here. Yeah, a whole lot of exercise. I'll skip them. It's an empty set. Empty set. Let me see. So this is an empty set, actually. This is the empty set. Let me see. Okay, empty set. Another important thing you need to remember is oh yeah, and subset. The concept of subset. So when we have a set, a subset means all the elements in the subset, it belongs to the whole set. All right, like do I use that? So 1, 2, 3. Okay, so all the elements of this set, it belongs to this set at the right side. So we can call it is a subset of this set on the right side. So so this is the example of subset. So the subsets can also be 1. Let's list some of them. 1 or 2, right? Or 3. They are all a subset of it. Or 1, 2, 1, 3, 2, 3. They are all a subset. 1, 3, 3. As long as it meets the it meets the condition that everything in this set, it also belongs to this set, it will be a subset of it. Okay, and one thing I want to remember you to remember is then the empty set. Where do I find it? Okay, here, the empty set. Empty set means nothing. Okay, empty, nothing. Easy. Yeah. So empty set is a subset of every set. It's a subset of every set. So if we want to list all the subset of 1, 2, and 3, so these are the 1, 2, 1, 2, 3, 1, 3, 2, 3, and empty set. Don't forget the empty set. Okay, remember empty set is a subset of every single set. Okay. Okay, so this is one way to say subset. Another way is this. Okay. This is also true because what's the difference between this and this? Between this two, this and this. The difference? Yeah. I have an equal. Yeah, so that's like less or equal, less or equal, and less. So this include the possibility of equal. So equal means like the same set. Okay. Yeah. Okay, so that's a subset, empty set. Okay. Let me see if there's anything else. Yeah. So this is another. We have a special name for it. It's called a proper subset. So which means it is a subset but not equal to that. Okay. So 1, 2 is a proper subset. There are a proper subset. Yeah. But 1, 2, 3 is not a proper subset. You can still say it's a subset of it. Yeah, it's tricky. It's still a subset. Like 1, 2, 3 is still a subset of 1, 2, 3, but it's not a proper subset. When we say proper subset, we exclude the possibility of equal. Right? Okay? Okay. Understand? So far so good? No question? Alright. Okay. Let me see. Maybe some other things here. Is the operate. Okay, so that's two different things. It's the union and intersection. Alright, that's just two examples. This is called union. Union means we take everything from this set, we take everything from the other set, we combine them together. Union. Basically, it's combine them. But since here, if we combine 1, 2 and 1, 2, 3, we have several duplicates, right? So the final product of this union is still 1, 2, 3. However, if we have 1, 2, 100, so the final product is going to be 1, 2, 3, 100. Okay. All right. So the final thing is going to be 1, 2, 3, 100. Like we take everything from here, we take everything from here, put them together. Union, simply speaking. And if it's another thing called intersection operator, which is this, like going up. Okay, union is like a U, yeah. So the other way is intersection. It's basically what you do is it's still the final product is still a set, but it's that the elements that those two sets have in common. Okay, so 1, 2, 100 and 1, 2, 3. What do they have in common?
1 and 2.
They all have 1 and 2. Yes, exactly. 1 and 2. So that's the intersection. We do not have we have 100 here, but 100 is not here, so that's not something common. Yeah, like the intersection. Yeah. And if it is okay, 1, 2, 3, 1, 2, and if it is like 9, what is this product here? No.
Like empty set.
Yeah, this empty set. Who use empty set here? Yes. Okay. Here, one more thing I want to talk is the difference operator. Like 1, 2, 3. If I exclude 2, 3, which means we're trying to find the difference between these two. Okay, the difference between these two. So what is difference between this set and this set? The common is 2 and 3, right? So if we use intersection, it's gonna be 2 and 3. But if we use this difference operator, it will give you the other way, which is the 1, because the 1 is the difference between these two sets. Like we remove, basically it's remove the second set from the first set. Okay, but if it's 100, is this still true? Yes. Yeah, because if we remove 100 from it, there's no 100 there, so it's still true. Yeah, that's an influence. And okay, I think, okay, last thing, I don't know if we're using that quite often, but it doesn't hurt to mention that it's a cross product of two sets. Okay, so the cross product of two sets is pretty simple. It's just you take element from the one element from the first and another and the one element from the second set and make it a pair. Okay, like so this is gonna be 1, 4, right? This is the first one, and 1, 5. And then 2, 4, 2, 5, 3, 4, 3, 5. Okay, so that's a cross product. And if you got like the cross product of more than 2 sets, it's gonna be here. It's gonna be not a pair. It's gonna be 3 numbers, like 1, 4, 4. Something like that. Yeah. Okay, so if it's a cross product of 3 sets, it's gonna be the element is gonna be 3 numbers, and it's first one from first number, second one from second set, first one from first set, second one from second set, third one from the third set. Okay, and like the permutation, but this is not very important in here in this course, but just want you to understand that. Okay, so basically that's what we learned about set, a review of set, so that we can use all those mathematic notions in our formal specifications. Later we learn. Okay. All right. Thank you very much. I will see you on Wednesday.